Okay, so I'm just going to go through a few things on the web page now. There's one little deal on module specs. So this is one particular, they call it high performance. This is a little bit old because if you come down here, it's 15% efficient. A lot of panels are getting closer to 20. And like I said, in Japan, there's a group there pushing 50. They're not into mass production yet, but it's possible. 20-year linear power output guarantee. So let's just see, when they say linear, let's just see what their losses are per year. Values. Per second. Okay, I am not seeing, well, this is their maximum operating temperature rated, and then let's convert that. So 50C, let's just see what that is in Fahrenheit really quick. My calculator button's not working on my machine either. Weird. Okay, 50 times 9 divided by 5 equals plus 32 equals $1.22, and that's getting right up there. So normally you don't have to worry about that. Temperature coefficient, so you're going to lose 0.4% per degree Celsius, or gain 0.43% for every degree below 49 or 47.9 you get. And this is how they partition those two. So most of the drop is coming in voltage rather than in current. Okay, so they got three strings of 20 cells with 3 bypass diodes. So the diodes, again, don't let the electricity flow back into the panel. And if we're looking at the power, so if we just look at this guy, 225, we can just sort of see how many watts each one of the cells is doing, right? So 225, so they got 3 separate strings in there, 225 divided by 3 equals, so 75 watts per string, 20 cells, 75 divided by 20 equals, yeah, so each little cell can do 3¼ watts. So here's the nominal voltage, nominal current. Obviously, the open circuit voltage is higher than that. The short circuit current is greater, but these two numbers multiplied together, the 28, let's just see what that is, the 28.9 times 779, 28.9 times 7.79 equals, that's how you're getting your 225 watts. Okay, and so some of them are down around 13.6. The reason you see the comma there instead of a period, because this is European. Europeans use commas instead. Okay, and there's that for a few other. Oh, this guy, maximum snow load, 550 kilograms per square meter. That's a lot. Yeah, that's 1,000 pounds of snow on 1 square meter, which, that if it was water, I mean, that basically means you could take your, a cubic meter of water weighs 1,000 kilograms, you could basically put a foot and a half of water on top of the panel and it would be okay. And if snow is, I don't know, 20% the density, you could put foot and a half, 5, 6 feet of snow on top of the panel, it'd be okay.
Well, they had pictures of a car parked, like a panel under each wheel.
Yeah. So, typically not an issue. Typically not an issue. Maximum wind load. Now the wind load is given in it's given in pressure rather than wind speed, but you can use Bernoulli's equation to solve that. I'm not going to go into it, but Bernoulli's equation gives you the relationship between pressure and velocity. So you can back out, if you know the velocity, you can find the pressure. Okay, so that's panels. Inverter specs, let's take a look at these. The Sunny Boy. Very popular. SMA, Sunny Boy, 3,000, 3,800. We've got an inverter just right next door. We've also got one out in our solar trailer. It's I think a much older version of the Sunny Boy. Okay, UL is the Underwriters Laboratory. IEEE is the Institute of Electrical and Electronics Engineers. These codes, 1741 and 1547, you can go look them up, and that basically says what the performance has to be in terms of insulation, safety, color, dimension, materials, performance, everything. 96.8 peak efficiency. That means, where's the rest of it going? Well, it's going to heat, because electrons flow through the thing and it gets hot. Opticool active temperature management system. I don't know exactly what that means, but it's more than likely some fins, some radiators in there, and perhaps some fans. Galvanic isolation, that basically means you're going to touch the outside, you're not going to get shocked. Patented automatic grid voltage detection. That's what a lot of the utilities will complain about. I don't want a bunch of solar out there on my grid because the grid goes down. I put my lineman up there and he gets zapped by your PV array that's pumping juice out. Well, this inverter says, hey, if there's no voltage, no line voltage, I'm not going to send any electricity out to the system. So that's that grid detection. Integrated DC connect switch, so you can just go and turn the thing off too, manually. So there's an automatic and then there's a manual as well. Now I don't know, but I believe, yeah, these numbers correlate roughly with the wattages. So the Sunny Boy 3000 is going to run 37, 50 watts total. The 3800 is up at 47.5, and the 4000 is up around pushing 5,000 watts. It's pretty good. They kind of under-promise, right? So the 3000 can give more power than 3,000 watts. It's good marketing strategy there. Max DC voltage, DC nominal voltage, MMP voltage range. Okay, so that's what we were talking about in that previous article, where if you are below 175 watts or above 400 watts, this thing shuts down. It's only going to operate in that range, and that's why sizing the array is pretty critical. But that's a pretty big range. I mean, that's a very generous range. Same thing with the start voltage. Until it sees that 175, it's not going to do anything at all. And that might be, if we saw previously that panel had was it 38 volts? So 38 volts. And if we look at this particular array, we're talking 175. So the very minimum you might get away with, so if we do 175 divided by more like 39, so you're going to want to have at least 5 panels in series to get this inverter cooking, and likely no more than 20. So that's a pretty big range between 5 and 20. Yeah. Okay. And I will admit, I am not familiar with every single one of these specs. But what you're going to want to do is say, hey, you'll go to the permitting agency, pull this and say, this is what, this is the specification that this particular inverter uses. This is kind of cool. You can do the RS-485 cable or Bluetooth. So you can actually have information sent to your handheld device with that. Looks like there is a little bit of consumption at 100 milliwatts at night, just to kind of keep the brain alive. I didn't realize this until very recently, teaching 214, but the grid will dynamically adjust its frequency based on demand. So if there's all of a sudden a little higher demand, the frequency goes up. It's like, oh, you need more energy? Okay, here it comes with frequency. If it goes down, the grid will diminish its frequency. So you can see right here, there's a range, 59.3 to 60.5 hertz. And so if all of a sudden Northwestern Energy detects an uptick, it'll pop that frequency up a little bit. So obviously actually this is pretty good. It says its power factor is 1. I'm a little surprised they claim that high with instead of 0.9 to some significant digits, but anyway. Power factor just means that they're not losing anything to stray amps and volts flowing out of the thing. So there's a one phase conductor, but they could do two separate phases, and the harmonics just means that they're always going to be within 4% of whatever the frequency happens to be. Yeah. So so if your inverter were 180 degrees out of phase with the grid, you'd get 0 volts. It has to be exactly in phase. So it's detecting that and following it to within 4%. Yeah. And that's a pretty tight range on the efficiency, 96 to 95. Okay. So there's your specs, and if so when you get to sizing the system, you have to take that into account, based on what the customer electricity demand is. Okay, that's good. I'm going to take a quick look at this, and then we'll look at the assignment together. This must be the one that this guy, Bill Brooks, professional engineer, wrote that he mentioned. Expedited permit process. This guy's done his homework. So you got the elevation, a high temperature, slightly more. So this is going back and looking at weather records.
Is there all things you need to provide to get an expedited permit, or is?
This is what he recommends, and it's going to be up to the local jurisdiction whether they'll use it or not. I think the idea is he's pulled data from the NEC and from ASHRAE and combined it into something quick so that the rest of us don't have to dig through all that stuff. So here's Minnesota, here's got Montana. Okay. Elevation, high temp, low temp, distance above the roof. Yeah, so check this out. Let's just go down to Billings, and you can see if your panels are closer to the roof, they're going to be a lot hotter than if they're 12 inches off the roof. So just like that little experiment I told you where we got the fans going to cool them, makes a difference. Airflow, that access to airflow. Even just yesterday, we were down at, and if you guys want to tag along, a week from Monday, Brian Jackson and I hope Brian Kearns are going to be down at Bitterroot Valley Greens firing up the Biomax, or at least looking at what needs to happen to fire up the Biomax. So if you guys want to get in on that, let me know, and I'll put you on that little expedition. Jackson has a 55,000 square foot set of greenhouses down there, and so he's always battling. Well, he's always working as in harmony with nature as he possibly can. Because he's got to keep the temperature, relatively consistent. You can't go too cold, and you cannot go too hot, or you kill your plants. And he was just using a temperature bath as a little experiment, because he's trying to get because as you know, water has a better heat capacity than air. A gallon of water holds a lot more thermal energy than air does. And so he's got this big pool inside, sort of his high dollar crop greenhouse, just to dampen the temperature fluctuations. He was doing something similar in a little bowl of water, and he had a coil heater sitting in there, and that was sitting on the concrete ground, which also has some pipes running through it to keep it warm or cool, just to regulate the temperature. And he was finding in this one tiny little dog dish size water a 20-degree temperature gradient, just in this little dish. And so I know I've talked a little bit about entropy in the past, but basically what he wants to be doing is entropicizing or mixing that water, because then it's all kind of the same temperature. It's the same thing. You've taken a bath before. You're like, it's too cold. Let's turn the hot on. Oh my God, my feet are burning down at that. So it's always amazing to me how great a temperature gradient you can actually have in a small body of water. And so again, each one of these numbers is just one single point. And I think the thing to keep in mind is that temperature, even though it's just a number, can fluctuate dramatically even in a small space. That's kind of the take-home message here. So if we look again at Bozeman, their high temp 38. Minnesota, I'm a little surprised to see that their high temp is actually lower. Billings, extreme min 27. St. Cloud, Minnesota, man, that must be up there. It's cold.
It's not too far north.
Yeah. See, they've got.
It gets cold up there.
They've got Missoula here too.
Came to the banana belt. Yeah.
I know. North Carolina. Okay, so this is something that he's compiled from a lot of different latitudes for temperature ranges. Well, let's look at the string sizing assignment. Might be a couple calculations we need to do in here. Oh, okay. So we were just looking at that previously. Yeah. So we already looked at the inverter, we already looked at the modules, and we just looked at the location on those 3 PDFs. So from here, it's filling in these blanks. So do that before looking at the. Let me get the answer. Again, this is voltage open circuit, so it's a panel with nothing attached to it. What happens to the module voltage as temperature decreases? I'll let you answer that. What PV design temperatures for Missoula? Okay, you can look those up too.
Most of that's just stuff we looked up on.
On those 3 PDFs we just looked at, yep. Calculate the maximum VOC. 13. Show your work for partial credit. Yep. So you'll want to figure out how the voltage changes as a function of temperature. And you'll come up with something. So let's just scratch your head on that a little bit. Sweet. Okay. So that's about it for this week. Take a quick peek at this guy. Article on ungrounded PV systems. I noticed the same thing in Japan. They did not have a ground switch on their outlets. Or one side was ground and the other one was hot, and they're just using the ground as their neutral. The same thing is true if you go into a panel. The neutral bus bar and the ground bus bar are connected in your sub panel in your house. See, grounded conductor and the neutral conductor. Ungrounded one. What's the benefit of being ungrounded though? I don't know. I don't get it. When they say bonded to ground, that just means electrically connected to ground. Floating, yeah. Oops. I just want to see what the motivation is. Okay, however, in the subsequent code cycle, this section was modified to clarify that this general requirement applies only to 2-wire systems over PV. Oh, okay. Accordingly, system grounding is not required. I just dropped off some money down at the Missoula Federal Credit Union today on the corner of Spruce and Orange, is it? Something like that, or Ryman?
Yeah.
Ryman. And the little parking meters are solar powered.
Yeah.
I dusted the snow off the one just so that, I don't know, it might be a little bit of solar penetration through the snow, but anyway, I dusted it off. It's kind of fun.
Yeah, I asked Greg about that,
Yeah.
and he said that he's got that in his house, and it snowed after he first got it. He was going up there and sweeping the snow off,
Found out it didn't matter.
and found out it was like 1%.
Still plenty of light coming through, yeah.
So he
Yeah.
said rather than risk his life on a snowy roof.
Yeah, one thing you don't see on these panels is what their band gap is, like what are the nanometers of photons they're sucking in. I just learned last night that, or yesterday, that bee eyeballs are most sensitive at 300 nanometers, which is a little bit UV.
Yeah.
It's a little higher frequency, higher energy, a little bit UV instead of infrared. Maybe that's just where the flowers are more towards the violet. Yeah.
You can see the pollen better.
Yeah, I guess it's kind of
It's
wild.
gotta have some evolutionary purpose.
I would think so. Yeah. Our eyeballs don't go that short of a frequency.
Few people do.
Maybe a few.
Particularly women, yeah, they're called like tetrachromatic.
Oh yeah, I've heard that. Yeah, tetrachromatic. Yeah.
Guy with pink to them.
Right.
Ultraviolet.
Different, yeah, rose-colored eyeballs, yeah.
Okay, so I have a question that's somewhat related to
Yeah.
this. Where would you go to find like the refractory characteristics of the glass that's on top of the panel?
So there's gonna be three different specs for the glass. Let me let's just dig through emissivity. I assume you mean like how much light comes through?
Yeah.
Yeah. Right, so here's, so there's emissivity, transmittance, and absorption. So the panel's either going to reflect, transmit, or absorb the photon. And this must be, this is at a given temperature.
Yeah.
So it's going to be a function of temperature, first of all. So this is just given at 300 Kelvin. Okay, let's just take a look at this. The emissivity coefficient, epsilon, indicates the radiation of heat from a gray body, according to Stefan Boltzmann law, compared to the radiation of heat from a black body. So it's what's the way to think of that? You know, and it's strange. I've never fully understood the reason for it, but apparently the sun, we kind of assume that the sun emits what's called black body radiation, and it emits across the full spectrum, some places more than others. And that's one, but for these other surfaces, let's just take a look through them. Alloy, aluminum, asbestos, asphalt is obviously it's absorbing a lot of that, and so you can see it. It's black. it's kind of the opposite of what you'd think, but that's why that number's so high. Basalt, let's just get down here to some glass.
And so this is essentially like the percentage of total radiation it absorbs, not specific to one set of wavelengths? Or?
This is going to be across the full spectrum. Yeah. And so glass is sitting at 0.92, 0.94. Yeah, this is a lot. Yeah, I don't look at this as much as I maybe should. Let's go look up at the black body mat. So I think let's look up glass emissivity spectrum. It's easier for me if I look at the let's just look at this guy for a second. Low E. So here we were talking before, visible light is, well, I just call it 400 to 700 nanometers. Okay, so this VLT is basically only going to let this amount of light through. The rest of it is just, it's kind of weird to think about, but it actually is kind of like a black body. You know, those other frequencies are reflected. So that's why once it comes through, all of these other frequencies bounce back off and stay in the room. Uncoated, low iron glass, much broader spectrum, so it's going to kind of let everything through. And so in terms of the total E, it's a function of wavelength. It's also a function of temperature. So I'm not 100% sure how you get from this curve to a single number, because obviously the emissivity is a function of wavelength, and it might just be the ratio of the areas under the curves for the whole thing. That would be my guess. I mean, that's how I would do it. So, yeah, I always have to look at a picture like this because I know that different. It's the same thing with the greenhouse effect. You could look at the absorption spectra for water, for CO2, other greenhouse gases, and each one of those is going to absorb or transmit as a function of frequency. So, but to do it, I would definitely go to the full spectrum. Every glass is a little different.
Yeah, I imagine you can engineer glass or another transparent material to allow and reflect different wavelengths.
Yeah, and I think what you'd really want, I mean, if you're going to design a nice glass to shed heat from your panels, you'd have a I don't know how. I mean, that's beyond my physics knowledge, but you'd allow it to transmit here, so the proper photons get down to the silicon. But you'd also allow it to transmit here, so the heat re-radiates away.
So
Yeah.
being absorbed,
Yeah.
so
Yeah.
like a super low absorption.
Exactly. Yeah.
factor.
Yeah. Yeah.
That's why I wondered, because I wonder if you could have like a liquid cooled panel with like a layer of water beneath the glass. And you'd have to look up the emissivity
For water.
Water.
Or some other fluid, or yeah.
Yeah, or some.
I like the liquid cooled idea. We've talked about this before with Jonathan Bowe and his geothermal course, is to have your PV coupled to your geothermal.
Yeah.
So if you got your 52-degree air beneath the ground, you're just sending that air again. And you could do it through this gap that you were talking about between your glass and your cells. I like that. Yeah. Keep them cool. Sweet. All right. Well, I'm going to wrap it up. Got a little meeting here at noon. I want to make sure I get these lectures posted. So thanks, everybody.